Hello, my name is Lucas Holt. I'm presenting on Spectre attacks. This is about the recent vulnerability that uh, all the major chip manufacturers have had that was announced in January. And this is on the paper about that. So, First, we're going to talk a little about the background, the main contribution of the Spectre paper, the questions and methods that the authors were trying to um, discuss, their results, weaknesses and next steps that should happen after a result of this paper, and the references. First, I'm going to talk a little about the background, um, how this works and exactly what Spectre is and the different parts of the processor that are involved in making that happen. First, we're going to talk a little about branch prediction. Modern CPUs will try to guess the memory location of a value after a branch is encountered to increase performance. Normally when a branch is encountered, there's a lookup table in the processor, and it checks to see if that has happened before and what the outcome was, and it kind of makes assumptions about if this state is true, then I'll need this value next, kind of an operation. So the CPU will discard any calculations that it makes if the retrieved value from its guess is incorrect. That's the general design of all processors since at least the Pentium in the 90s have done branch prediction. So speculative execution is kind of related to that. So it's a technique used by high-speed processors in order to increase performance by guessing future execution paths. So in addition to retrieving values like branch prediction does, it also will yeah, the Facebook thing. It also will allow you to um, run additional code, so additional instructions can get run and executed using this approach. So it's kind of a combination of branch prediction and speculative execution together allows processors to go at a high rate of speed. So the attack is around um, tricking the processor into loading additional memory from the address space of the program that would not normally be accessible. Um, so a good example of this is say that you're running a virtual machine, Amazon, for instance, and they have this server that has, 20 VMs running it and different customers' accounts. If someone is able to exploit this, they could get the hypervisors, which is a program running on the system. Potentially, they could get that to execute and read all the customer's memory on the server. Or as another example, say that you have a web browser and you're going to a web page and someone can inject malicious JavaScript into your browser. Not only can they read the information on that current website, but they could also potentially read information that you have in other tabs. So say you have your bank account open or you have your email, so they can see all your current Gmail that you have on the screen, something like that. So there's several devices affected. Basically, every modern processor from Intel, AMD, and ARM is affected. CPUs will need to be completely redesigned in terms of how they do branch prediction and speculative execution to prevent this vulnerability. And additionally, software will probably need to be changed to make less assumptions about the security around certain operations within the processor. So a couple of other concepts come up in this paper. Side channel attacks, which is kind of the side effects that happen when you run an operation on a computer. Um, Examples of this include like power consumption. So like when you run certain instructions or do certain operations in your computer, it may increase or decrease the amount of power used. Um, there could be radiation or even the noise level. Potentially there could be a slightly different noise or sound that happens. Those are physical aspects of side channel attacks. There's also another concept where you can do it kind of at a software level. So you can look for certain states that things are in at the software level to determine if certain operations have happened. So on a CPU, this can be like a micro-channel architecture attack where you look at the timings for caches, so that the differences between, say, L1 cache and L2 cache, and when data transfers between one or the other. So the concept behind Spectre is that you basically trick operations to happen, and then you pull the data out of the cache because the cache is not always flushed in all cases. And that's kind of how the entire thing works. So next we're going to look at the questions and methods. So first, the authors want to know if there was an easy method to attack the speculative execution engine in a modern CPU. They want to show that they can get access to memory locations within the CPU, within the address space of a program. Next, we want to see if we can read the entire memory of a program. So, say you have your web browser or a web server or really any application that could possibly run on a computer, and you want to see if you can get access to it. Maybe you have secured keys, like a secure shell client has your key in it, and they can get access to it. Things like that. They wanted to see if it was exploitable with JavaScript. So is this something that can be run in a web browser and you can escape the sandbox of the modern browsers like Chrome or Firefox have and actually get access to all of the information in the person's web browser at that point in time? Maybe they have another tab open with their Google account or their bank account or something of that nature. So we're going to talk a little about the techniques here. So the first step is to find a sequence of instructions that you can execute to get access to the address space of the program. So this is like the shared libraries that you have. Hypothetically, say you're on a Linux system. There's a bunch of instructions in libc or other libraries that the program runs frequently, and those instructions in turn can have access to certain parts of the memory address space within the program while you're running it. So you look for certain combinations of those instructions that give you access to a broad range of memory locations within an application. The next step is that you trick the program into running those instructions. So the third step is to gather the data from the secondary cache, which isn't always reverted by the execution engine. So the general idea here is that you run some legitimate code a couple of times so that the branch predictor on your CPU core is kind of assuming that a certain case will happen where these instructions are fired. And then you give an invalid answer, which tricks the processor into going to a weird memory location, but still predicting that the path is correct. That's generally how you get access to the memory. And then those memory locations will get reverted at the CPU level when it realizes that the prediction was wrong, but it will not get cleared from your L2 or L3 cache in your processor. So the attacker has access to that and can get the information out. So here's an example of an actual code block where you could have an exploit. So the first time you run this, you would give a valid value for X that's within the array, and you could run that potentially a couple times, maybe on multiple threads on your CPU to get all the cores kind of primed for branch prediction. And then you do an invalid instruction where you give it a weird memory address for X. And then when that if statement evaluates, it will assume that the branch is correct and execute the next line of code, and it will read a bad part of memory. And that will give you access to something sensitive. So now we're going to look at the results. So the authors of this paper proved that they did some testing on multiple processors, and they concluded that at least Intel Skylake, Haswell, and Ivy Bridge processors have been vulnerable. Since the paper has come out, they've also confirmed that 8th gen Intel processors are also vulnerable. Additionally, they tested AMD Ryzen processors, and they found them to be vulnerable. Other people have tested older chips like the FX series for Bulldozer and so on, and those are also exploitable. And additionally, ARM chips from Samsung and Qualcomm have been tested, and they're vulnerable for certain models of newer phones. So in the ARM world, speculative execution is kind of a new feature. So a lot of the older ARM chips don't have that feature, and it's kind of in the newer phones. So it's a smaller number of devices on the ARM side that are affected by this, but they're still there. So another thing that comes up with this discussion is Meltdown, which is another vulnerability that was released at the same time. Meltdown does not use branch prediction like Spectre does. It uses instructions that cause a trap instead. Meltdown exploits basically kernel memory, so um, it's tricking basically information leaked from the kernel level into user land. So it's a little bit different, and there were some patches that are already out for that for compilers. So both GCC and LLVM CLang have a patch in their like latest bleeding edge versions that allow you to kind of mitigate Meltdown. Neither of those compiler changes will help you with Spectre, so you're still vulnerable for that. So the branch prediction problems. So the branch predictor in a Haswell CPU only uses the 30 least significant bits of the branch to index, like in what they call the branch target buffer. This is kind of like space in the processor to kind of keep track of branch predictions. It's the table for it, and basically it only keeps track of target addresses for certain operations. So this is a really simplistic model that's been used for 20 plus years, and it needs to be changed in order to mitigate this problem. We also have side channel attacks. So an attacker can use a flush and reload attack to figure out the timings of the different cache levels, and that allows them to kind of guess when things are going to show up in L3 cache where they can kind of get it out. So here's an example in Chrome. So you can see that this is a JavaScript exploit. This allows us to get out of the sandbox in the browser, and this is the individual instructions that are actually run in the processor. So one mitigation that was found in some Intel chips is there's an mfence and lfence instruction that allows you to kind of like run code serially on the CPU. So you can kind of protect, kind of like a pthread, kind of like doing a semaphore and protecting a region of space so that it only runs on one core. So you can kind of do the same approach using these instructions on some Intel chips, and it seems to mitigate the problem. This has not been proven to be the same effect on AMD chips, so it's not a generalized mitigation, and it's not even necessarily guaranteed on all models of Intel chips. So the next steps is to investigate serialization mitigation on AMD and ARM chips to understand if there's any workarounds, to evaluate possible microcode updates that might mitigate some of the problems with this, look into the possibility of a new branch predictor or speculative execution engine design that may mitigate the problem. And AMD Ryzen chips have a completely new speculative engine that's supposed to be cutting edge, and it hasn't widely understood how that works yet, so looking into that. So the key takeaways here are CPUs cannot be trusted to run sanity checks for virtualized or sandbox environments when speculative execution is used. So basically all modern processors plus virtualization equals a problem. These attacks are easier to issue on systems with less threads and cores. So when you're running it, if you bounce around between different cores, the branch predictor is different in each core or in each physical CPU if it's a multi-socket system. So that's why a lot of these attacks run a bunch of threads to try to get all of the processor cores trained. CPUs from Intel, AMD, and ARM are vulnerable, and CPU vendors must explain the security ramifications of using different instructions. Here's the reference for the paper, and I'm really glad I was able to present this to you today. It's a really interesting topic, and it's rather current. It just came out in January, so I hope you enjoyed it. Thanks.